So in this video, I want to discuss the end of chapter 7. We've been studying the Laplace transform, and the last two sections introduce a few new properties. First, I'll begin with operational properties from 7.3, and reviewing that's already been in your homework. I'll also discuss 7.4 and the Dirac delta function in 7.5. So first of all, in 7.3, we are introduced to the first translation theorem. Now this theorem says that if you already know the Laplace transform of a function, so we're familiar with the property of a particular function, for a constant a, so a is any real number, then the Laplace transform of the product of e to the at times a function f of t, so this would be an exponential times a function you are already familiar with. Then the good news is that the Laplace transform of that product, you don't have to plug into the integral and use integration by parts anymore. If you look at that property in 7.3, this is actually going to be the Laplace transform evaluated at s minus a. So this is in 7.3. You've been practicing these problems. Here is an example, or here rather than that, here is the various notation that we might use. So the Laplace transform of that product, you might see this written as the Laplace transform of the function, and because that will be a function in terms of s, you'll evaluate that at s minus a. The inverse Laplace transform, so because this is a one-to-one function, or one-to-one transform, then the inverse, if you can write a function completely in terms of s minus a, and it is in that form, you recognize it is the inverse Laplace transform of a function, or it is the Laplace transform of a function, then you can simply take the inverse of that expression in terms of s and multiply by e to the at, so that you get the product. So the first translation theorem, a couple more examples. So you'll notice I have the theorems or the properties written right here just to reference. Here I had e to the 2t times cosine. Now I could have used the definition, plugged that in, and found the Laplace transform, but what these properties are saying are that because I have an exponential e to the 2t, and I recognize I already know the Laplace transform of cosine of 2t, I'll simply take the Laplace transform of cosine of 2t and substitute for all of the s's, s minus 2, so that I get an expression like this. For the inverse, I recognize this is 5 over something squared, kind of like 5 over s squared. So here I've factored out a 5, written the Laplace transform of 1 over s squared. And because that was in terms of s minus 3, I've multiplied by e to the negative 3t to represent that translation. So my final solution would be 5t e to the negative 3t. I want to remind you of the Heaviside function as well. So the Heaviside function is defined to be it's unit step function. So u of t minus a, it's exactly 0 before a. After a, so for t greater than or equal to a, then the unit step function is defined to be 1. Now this graph, sometimes when you graph this in Sage Math, it may look like these are connected, but they are not. This is a piecewise function defined as such. And once you understand the unit step function, or the Heaviside function, then the second translation theorem says that if you, again, know the Laplace transform of a function for a constant a greater than 0, so we will use this for only starting from values 0 to greater for this theorem, by the way. The Laplace transform of the product of a function evaluated at t minus a times the unit step function at t minus a is equal to, you'll notice this is in terms of s, it's not the same as the last property we were looking at, but this is equal to e to the negative as times f of s. This comes from using the definition and substituting 0 in on this particular interval and 1 in on the interval indicated. So this is the second translation theorem. I'll work an example. Here you were given, so here's the property. Here I want to take the Laplace transform of this product 3t minus 15 times the unit step function at t minus 5. Now that is not currently, it's not exactly in this form, but I do recognize if I factor out a 3, I would have 3 times a function in terms of t minus 5 times the unit step function in t minus 5. You'll notice this predetermines how you'll have to rewrite your function. So once I factor out the 3, then I am able to use the property. I have e to the negative a, so I'll have e to the negative 5s times the Laplace transform of, because this was a function, this is your f t minus 5 is equal to 3 times t minus 5, then my f of t was simply 3t. So I still need to take the Laplace transform of t, that's 1 over s squared. This product here is your Laplace transform. For the second example I wrote, I want to take the Laplace transform of this product 2t times unit step function of t minus 5. Now, and this example, you'll notice I used an uppercase and lowercase, that I just accidentally missed that, but don't let that confuse you. Some textbooks or notations will vary, and I changed most of these but just left that, so don't let that confuse you. Here, 2t is not in terms of t minus 5, so we must regroup this using crafty methods. You'll notice what I did down here is I added and subtracted 10t. Added and subtracted 10. So you'll notice I have 2t minus 5, so minus 5 in parentheses here, that negative 5 times 2 would be negative 10. So on this, it's different because I've subtracted 10. So I've added 10u on the right side. If you take a minute, pause the video, you'll notice this line is exactly the same to the bolded print that I have here. So take a minute. The reason I'm doing that is so that I have it in the form to use as property. This statement is in that form. So that now using the property f of t minus a, my f of t is 2t. So this will be the Laplace transform of that first piece. 10 unit step of t minus 5. Fortunately, the Laplace transform of u of t minus 5 is e to the negative 5s all over s for the 10, the constant. So that's saying that f of t minus a in that case would be 1, and the Laplace transform of 1 is 1 over s. So there are 2 examples using the second translation theorem. In 7.4, we learn new operational properties. To begin, in 7.4, our first property is, we have here again the Laplace transform of a function, if you're familiar with that, and remember that this says n is a positive integer, so 1, 2, 3, 4, 5. Then the Laplace transform of a product of t to a power times f of t. This could be t to the second, t to the third, etc. Then what you'll have is negative 1 to the nth, so it will either be positive or negative depending on whether n is even or odd, and the nth derivative of the Laplace transform of f. So this property, there are going to be some cases now. When you're using this property, you actually could make a choice in using this property versus some of the others on some particular functions, but this is a new property that allows you to, it'll kind of simplify your life for some of the more complicated ones. I want you to take a look in the book. This isn't a very difficult proof to work up. I didn't build it into this set of slides, but really this comes from taking some patterns. So if you look at this, you could actually prove this by induction. So you could do this to t to the first degree, t to the second degree, and then you'll be able to build this property from that. So using this property in this example, here I have t e to the negative 2t. This is actually an example where I could have used one of the previous properties. However, in this example, because this is t to the first degree, then I'll have negative 1 to the first degree. The first derivative, so this is another step that I left out and didn't catch until now, d ds is what I should have here. So d ds, the first derivative of the Laplace transform of e to the negative 2t. This will be negative d ds of, here I have the Laplace transform of e to the negative 2t, and I will take the derivative of that. When you take the derivative, this is the expression, the quantity s plus 2 to the negative first degree. So when you take the derivative, that negative 1 cancels this negative 1, so that you have the quantity s plus 2 to the negative second degree, and that is what I have here on the right. You all will practice this for numbers 3 and 7 and 7.4. The next thing I want to do is introduce the operation of convolution. Now this is somewhat, in the last section we learned about the Heaviside function. Here, this is an operation between two functions that are continuous on the interval 0 to infinity. So if you remember f in this notation, it means that f and g are in the class of continuous functions on this interval. If you have such an f of g, then we use this star operation, so f star g, when f is convoluted with g, so we call this the convolution of f and g, then this is defined to be the integral. You'll notice my variables here, so 0 to t is an independent variable, but I have this function in terms of tau, so f of tau times g of t minus tau. And I think I have this appearing some side. I'd like you to practice these, to practice this idea to get a feel for it. This is actually a commutative operation, meaning that just like 3 plus 4 is equal to 4 plus 3 because addition is commutative over the reals, then this operation is commutative over the C1 class of functions. A couple examples, t star g, sine. So the convolution of t and sine of t. Here I have, since t was first, I've substituted, so my function f of tau, if f of t is equal to t, then this would be f of tau equals tau, so t times sine of, and here my second function is in terms of t minus tau, so I have sine of t minus tau there. On my next example, so cosine star t. Here, because cosine was first, I have cosine evaluated at tau, and my second function would be t minus tau. Thirdly, I have 3 times sine, so this is the convolution of 3 and sine. 3 evaluated at t would, or at tau, 3 evaluated at tau would simply be 3, and sine of t evaluated at t minus tau is sine of t minus tau. Now, for each of these examples, if I wanted to work with them, I could of course integrate. Keep in mind you're integrating over the you're integrating with respect to tau. In this last example, I've gone in the other direction. Often you might need to understand the property in the opposite direction. So the integral, here I have from 0 to t, e to tau, d tau. Because there is no function in terms of t minus tau, I'd actually say I have an error here. It's not, this isn't untrue, but I don't like the order that I wrote that in, so I'll also make a change on that. Because this function is in terms of tau, then that will be my f, and so I would have put e to the t, and then star 1 would be my function in terms of t minus tau. Because this is actually a commutative operation, that isn't incorrect, but I do want to make sure that I make that comment at least. Once you understand convolution, the operation, then the theorem we will use in this section is actually quite satisfying, so I think you'll like using this. This would perhaps be one that you might try to use most frequently after you get a feel for it. So for f and g of exponential order, then the Laplace transform of the convolution of f and g is equal to just the product of those. So again, I'm not saying f times g, it must be this operation, but if you have the convolution of f and g, then the good news is the Laplace transform of that is simply the product of the Laplace transforms of your two functions. And the inverse, if you can recognize that when you have a product in terms of s, you have the inverse Laplace transforms of two functions, then that will simply result in the convolution of f and g. to practice these ideas, so to practice understanding the convolution operation and the theorem I have here, you will work these examples from the textbook. Now these all are odds, so you can check your book, and I will also post some of my solutions. Now this is differential equations, so we want to focus on differential equations, but now that we're learning about the convolution operation, you can actually apply this to solving particular types of equations that have this form. So these properties can be used to solve what we call Volterra integral equations, which have the form you see here. In order to solve one of these, so I want to solve for f of t, I apply the Laplace transform of both sides. So here is my example. Apply the Laplace transform to both sides so that I have the Laplace transform of f. This is the convolution of, since it's f of tau, it would be the convolution of f of t time star 1. So you'll notice when I took the transform of that, then I have the Laplace transform of 1 times the Laplace transform of f of t. This is equal to the Laplace transform of 1, which is 1 over s. Algebraically, so simplifying that, I combine the f of s's, the Laplace transform of f of t. Anything else I put on the opposite side. So you'll notice when you factor out an f of s here, you'd have 1 plus 1 over s. The reciprocal of that is s over s plus 1, so I've multiplied by that reciprocal so that I can isolate f of s. I now cancel the s's, and to find f of t, I simply apply the inverse Laplace transform of both sides so that I have e to the negative t. I have assigned two similar equations, number 37 and 39. I believe 39 had some difficult partial fraction decomposition, but remember that I put out a video last week how you can use Sage Math to help you if you find that difficult. The next property that I'll discuss is the transform property of a periodic function. So you'll remember from trigonometry, sine, cosine, they are periodic functions. If you have a piecewise continuous function with period t, and it is of exponential order, then the Laplace transform of such a function would be given by this. And I actually encourage you to look up this property as well. The textbook has a nice little explanation for why this works. Right now I'm focusing on how to apply these, and so on the right side what you'll notice I have this quotient 1 over the quantity 1 minus e to the negative s capital T. That capital T is not your variable here. It's actually a constant. It's the period of your function, f of t. I realize there are a lot of t's. Sometimes mathematicians don't think that through, but this t again is a constant. So depending on whether you have a graph or whether you have information, you get that value from the prompt. Once you have that, then you'll notice on the right side I have the Laplace transform notation basically from the definition here. The only thing that's different is this term that's on the outside, and instead of going from 0 to infinity, we have 0 to the end of one period. Lastly, I'll talk about the Dirac delta function. So in 7.5, we are introduced to a new function, and I say function with hesitation. This is a generalized function. So what that means is, this is almost more theoretical than a function I would teach my college algebra students, for example. What the Dirac delta function is, so we use this delta here, it's defined to be a function. So here I have delta of t minus t naught for some constant at a particular value, but 0 everywhere else. What this might remind you is a bolt of lightning, an instantaneous bolt of lightning hitting something so that it sends an infinite amount of power at a particular second, but nothing more, and at no other time is there any power sent to that object. The generalized function called the Dirac delta function has a property such that when you integrate from 0 to infinity, you have this area is equal to 1. . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . looking at 7.5, I want you all to read through this proof. I'm actually not giving you a bunch of homework because I felt like it was somewhat repetitive, but I do want you to look at the proof for why this is the case. The Laplace transform of the Dirac delta function at t naught, so t minus t naught, is equal to e to the negative s t naught. An example for that, if this is t minus 0, then the Laplace transform of the Dirac delta function is simply e to the negative s. For a second example, if we have t minus 2, then the Laplace transform of that Dirac delta function is e to the negative 2s. You could use, so this will be your homework. Please read these 2 pages, work through the quick proof to understand why that's the case, and I've only assigned 1 problem from that section. In Sage Math, the function is denoted Dirac underscore delta. So you'll notice this was the code that I entered into Sage Math, and this was the output, and this was the example I had on the previous slide. So if you want to use Sage Math to help you check some of your work, then that would be the function. And you could always Google Dirac underscore delta Sage Math to get more hints for code or more snippet. So best of luck. This was to end our conversation about chapter 7. In our next video, we will discuss chapter 8. Thank you.